my talk will be to talk about what are we been doing about exploring the AI and machine learning in telecommunications. So this is work done with collaboration with Fernando Guilmar, also with the PhD students, the Beatriz Oliveira, Manuel Neves, and Marco Fernandes. So let's start doing a short introduction of IT. So IT is a non-profit organization. So we started in 1995. We are associated laboratory from the beginning of this century. So what are our main mission is to create and disseminate scientific knowledge, support advanced training, and also to promote technology transfer, and also to support public policy. We have different groups. We are called research lines. We put here, just take this out. So we have different thematic lines, including wireless technologies, optics, and photonics. We have also the information data science. And let me find it here. Information data science, network and service, and also the basic science and enabled technologies. In total, we have more than 200 researchers. We have approximately 70 wired PhDs, 7 are permanent, but this is increasing a lot last year, and now approximately 150 PhD students. Okay, in terms of our group, the optical communication systems and networking in Aveiro, we have been working in several areas. So from the single carrier to digital subcarrier multiplexing, the detection, current systems, all part of digital signal processing for optical communications, all part of the transmission wire, joint carrier phase recovery, advanced motion formats that we'll also see, and amplifierless current optical links, free space optics, visible light communications, and also all related with optical networking, fixed mobile conversion, PON, and radio over fiber systems, and also including sensing systems, which are integrating the sensing and communications, and the current MIMO radio network enabled by photonics. There are some that we'll talk in this talk. We are not talking all, but also can be using the AI, machine learning, and also deep learning. Like we'll talk today in the part of single carrier, current systems, digital signal processing for optical systems, the part of advanced simulation formats, the autoencoders. We also talk about amplifierless current optical links and free space optics. So these are the main topics that we are addressing, the part of AI and machine learning and deep learning. So our group, we have 4 researchers, and at this moment, and 7 PhD students, and also we have also the MSc students. So in terms of our work in part of exploring AI and machine learning in optical wireless communications, so let me first a brief introduction. So up to the fourth generation, we have been using the sub-6 GHz spectrum bands. So 5G is now extended 4G with millimeter wave frequencies. And we are expecting that 6G is expected to extend millimeter wave to terahertz frequencies above 300. We believe that free space optics in infrared region can be an attractive alternative to terahertz wave. Why? Because there are a lot of main advantages of free space optics, since you can use many fiber components like the transmitters, receivers, and filters. And all driving electrons are in Ethernet baseband, no need for complex and expensive amplifiers and filters and mixers. We have a higher carrier frequency, which enables very high bandwidth and wireless transmission capacity. And also these are very high directivity. So we can also have a very physical layer security, and individually unlimited spatial division multiplexing. And also we are using, until now, unlicensed frequency bands. Nevertheless, with the adoption of free space optics, still faced some critical challenge. These challenges are the impact of the turbulence on link power budget, which is still largely unknown. We also have the impact of the pointing errors, which requires a very accurate beam steering, and also need to improve the link capacity and reliability. So I think here AI can help on this work. For sure, we also, in terms of high capacity, today we have very high capacity pluggables, and also we can make the seamless with the fiber FSO. So by using just optical collimators, so optical collimators, they perform the seamless between fiber to wireless conversion. So you don't need for electrical optical or and optical electrical conversion. So it can be transparent to the bit rate and modulation. So we have the full fiber bandwidth is preserved and can be compatible with the WDM. This is one of the last field trials where we, in Aveiro, we have experimental 3.6 terabit per second transmission over 1.8 kilometers. So we are linking the two buildings, IT and PCI, at this distance, and we were quite successful the transmission over this long distance, and with this very high capacity, which is very difficult to get this transmission rate in a millimeter wave and also in terahertz. For sure, we need to find good resilience. The one problem as the free space is the weather conditions. So you should find weather resilience by using adaptive modulation. So here, one of our works is using probabilistic constellation shaping. So the probabilistic constellation shaping, you can adapt, take into account the weather conditions if you have rain or fog. So basically, by this way, it will be possible to adjust the transmission rate by adjusting the modulation, taking into account the channel conditions. By these ways, we can get some gain. So taking into account if you are, for example, some experimental results at 400G or higher for 400G from 400 to 5G. So we can adapt the transmission rate, take into account if you have a good weather or bad weather, like rain, and by this way you can have some accumulate capacity gain. We haven't shown that by this way we can get more than 80 terabytes of accumulated capacity over 3 hours, over fixed 400G modulation, and more than 50 terabytes of accumulated capacity over 500G modulation. But for this, also, it's very good to have a good channel estimation. So this is for an example where we have here the optical power for when you have the sunny weather and also the rainy weather. But also you can see there's some autocorrelation for it more than when we have for rainy weather. So we can predict the channel and estimate, and this by the estimation we can adapt the modulation format, take into account the channel conditions. So an outdoor FSO channel will be subject to the time varying impairments related with different kind of turbulence. We have from the fast fading, which can result from atmospheric turbulence with coherence times between 1 to 10 milliseconds, and also we have the slow fading, which can result from weather change and also the pointing error. So we will try to compensate this. So the ideal FSO channel estimation will be to model both the effects of accurate predict the channel state. And so for this part, we are using, for example, artificial neural network channel estimation, where we can training the network, take into account of the channel, and also to predict the channel, the coherency. So basically, so we have like a black box modeling. So the proposed methodology is collecting several batches of attenuation data with a rate enough to observe the coherence time. We are using this collected data to train an artificial neural network. And after this artificial network is trained to estimate the next channel attenuation. By this way, we can try to compensate the fluctuations in terms of attenuation and also to predict the channel condition. So we are using here a fast optical meter after the channel estimate, which can control the output power in terms of link. So this is one of our experimental tests. We are using this is in the top of IT. In this case, we have a distance of 15 meters. We are using here 60 gigabaud and 16 QAM and 400 gigabit per second. So we have here some limitation because we are using MATLAB. So the time limitation is imposed by the component interface like MATLAB. So we are using just in this case 20 samples per second. So we can compensate the slow variation, not very fast. Probably we need to, the next step is using FPGA instead of MATLAB to have a more robust and real-time compensation of fast fluctuations. So the goal is to using the artificial neural network to estimate or to compensate the slow fading effects, thus equalizing the receiver power. And this is show some here, some examples where we have the power fluctuations. The fast power fluctuations are only partially compensated due to limited sampling rates, but the slow fading is largely compensated by the proposed scheme, resulting in an average receiver power that is wholly constant. By this way, without this power compensation, the average receiver power can vary almost 10 dBs. So, but this is one way that we can use to compensate the link for different weather conditions. And also, we did some experimental validation. In this case, with adaptive power control. So the pair measurements were obtained during the daytime. And considering, for example, the threshold of 400 ZR, 1.25 times 10 up -2, we can get a reliability of 99%. So this result shows that the free space optic is a robust solution when the channel is properly compensated. Another application of free space optics, it can be for data centers, interconnect. So the free space optics appears as a candidate for using because we can avoid a lot of wiring, optical fiber wiring. So we can reduce the cabling and complexity. We can try to also to adapt the traffic through deep steering, and also can reduce the latency and footprint and power consumption. But one of the main problems in free space optics inside data center we need to require a tight and precise beam alignment. Because the better aligned system can completely compromise the system. This is one example that I show here. So you need a very robust acquisition tracking endpoint. and also powerful techniques that must be used to reduce the impact of pointing errors. For one example here, see if you have just 1 millimeter deviation, and in this case of the beam horizontal displacement, we can have more than minus 20 dBs of attenuation. So we need to find very good and reliable acquisition tracking point, and also we need to adapt the modulation format, taking into account if the beam is not correct alignment. So this is one example. In this case, we are using here, in terms of optimization, you are using a particular swarm optimization to do this alignment. So by using a particular swarm with a gimbal system, we try to attract it and get the best alignment of the system. This is one of our experiments, and 1 terabit per second free space optic. So this case is for short reach. We are using this only for 3 meters, where we demonstrate, but for sure it can be for a long reach. So the process is the same, so since attenuation it's quite low. In this case, you use 64 pm probabilistic constellation shaping with a symbol rate of 100 gigabaud. So the idea is the goal is to use the probabilistic constellation shaping to adjust the bit rate to account for sequential beam misalignment, and also to using all parts the alignment of the beam. So by this we have two options. One is to adjust the modulation format, take into account if it's not our correct alignment, but also, so by this we can, by using probabilistic constellation shape adaptation, we can mitigate the pointing errors, keeping the performance constant through the bitrate adaptation. But in case of if you have extreme power loss, we can act in an acquisition tracking pointing system in order to return the system to the maximum performance. In terms of the other topic that we've been working is in autoencoders for unamplified optical links. So with increased data rate requires on short reach links like data center interconnects. So the current systems are expanding to those short reach systems like these from these optical transceivers for 400 gigabit Ethernet, but also there are also study groups such as IEEE Beyond 400G and OAF 800G coherent, where also they are exploring even higher speed connectivity standardization. Okay, so in terms of the coherents, why are you using the coherent receivers? Because they are very robust. We can have very good sensitivity. They are tunable, but for sure we still requires for short reach, low complexity, cost, and power consumption. One way to avoid will reduce the cost and power consumption, and also the complexity, is to remove the optical amplifiers at transmitter side, so the booster. So that one option is to remove this booster. So by this way you can reduce the power consumption and also the cost. However, if you remove the booster, we have a peak power constraint in this case. So usually the conventional constellations we are using are suboptimal. So the idea is to using autoencoders based on geometric constellation shaping. This one of so the idea is to using an artificial neural network at transmitter and not at the receiver, where we are try to get the best constellation. So by this was also using a symbol-wise implementation that was based on TensorFlow and using Adam optimizer, and the loss function is cross entropy. So this was one work. So we use this for different modulation orders from 8, 16, 32 up to 128. So I don't have time to show all the results, but you can find in our reference. By this way, we can training and after try to get the best constellations for a PRPR reduction. So by this way, we and also after to get the constellations, the optimal constellations obtained by the autoencoder, we validate experimentally in terms of performance. So this is one example where we are using in our setup after where we have here our arbitral waveform generation, the IQ dual polarization IQ modulator. After since this is only for, we are using low power transmission, so you don't need to take into account nonlinear effects. So our channel inlet here is just it's a VOA. So we are using here a current receiver, and after we're doing all acquisition by using 4 oscilloscopes with 200 gigasamples. So this is one example. So we have another examples in publication. So this is only for in case of 8 QAM. There's some problem.
Yeah, Paulo, we lost your screen.
Why? Okay.
But we can see you.
So I don't know what happened. Maybe I can start. Do you know which slide I am? Okay.
Yes, we can see it. It's on the first slide.
Okay, let me do what happened. So
it's all Microsoft's fault.
okay, so I was stopped. Maybe let's see. Okay, I'll talk about autoencoders to find, I think it was here, in part of the geometric constellation shaping. So what I say that you are using geometric constellation shaping in this case of amplify current optical links to find the best constellations, and after getting by the autoencoders, we are validate experimentally and take our results. I think that I was here in my explanation. This is one example where for 8 QAM, for sure, if you compare 8 QAM with 8 PSK, we already have them in terms of peak to average power ratio less than 1.9 dBs. But if you compare it with our constellation by using autoencoders, we have a gain of 3.1 dBs. And for sure, this gain in peak to average power rate in this reduction will have it will be translated into power budget gain, as you can see here. So for at autoencoded gain of 3 dBs, you have an auto gain of 3 dBs relative to QAM, and also 2 dBs relative to PSK, which allows an increase of distance of 13.6 kilometers. Another topic that we have been worked at this moment, it was in a this is one of more recent work by Mark Fernandes. He was in multi-parameter AI-based bandwidth compensation. So with the demand of capacity is continually increasing, and techniques are needed to develop to mitigate the bandwidth limitations. We have the limitations of ADCs, the DACs, and also the optoelectronic components. So one way to make the bandwidth compensation is using using pre-emphasis. By these ways, we also enhanced the high frequencies and also maybe the low frequencies in order to compensate the attenuation. However, if these band limitations are properly compensated by pre-emphasis, we show that increase the significant PRPR, which will degrade the performance. So we have been studying by this problem, by dividing the problem, not make all the pre-emphasis at the transmitter side, but divide by in a transmitter and the receiver side. So I'm dividing the problem, but we still need to know how much compensation in which filter should apply. By this one, we are also in terms of concept of implementation. So the idea is to get a system inverse transfer function of the whole complete system. We are dividing the field into multi-sections in order to make the optimization. And after we divide, so we duplicate the filter for transmitter and receiver and attribute a height to each section. So for the initial is considered, so we have the initial field compensate of the bandwidth limitations. But by these ways, we are using particle swarm optimization in order to calculate the height of the filters for the transmitter side and the receiver side in order to maximize the performance. So this is one example. We are using 800 gigabit per second transmission. So by this way, we are trying to compensate the filter transmitter and receiver side by using particle swarm optimization. In this case, we are using a DWG. The DWG, which has approximately 45 gigahertz of bandwidth, which is 120 gigasamples of rate. We are using here probabilistic constellation shaping of 64 QAM. So with 800G, and by using this week, take the account of the modulation, we can have from 90 to 100 gigabaud. Our modulator has approximately 40 gigahertz of bandwidth. Our current receiver, approximately 70 gigahertz. Since we are now trying to compensate, these are some limitations in terms of bandwidth. And our oscilloscopes acquisition, so you have approximately 70 gigahertz of bandwidth with 200 gigasamples in terms of sampling rate. So we are trying to compensate the filter at the transmitter side and also at the receiver side. So we compare the gains. So we compare the gains without any compensation, and also in terms of the symbol height. And we can see if without using compensation, we can get a gain starting from, depends of the symbol height they are using, starting from 0.5 dBs, which can reach values above the 2 dBs. When considering only the receiver, the receiver filter automatically presents a gain of 1.5 dBs, and also compared with only the transmitter filter, the proposed optimization presents a gain higher than 1 dB over the typical transmitter pre-emphasis. When you are using the same filter transmitter and receiver side, we have a gain of 0.002 dBs. So this is what we'll show in terms of what we can do in the what we've been doing in AI, machine learning, and deep learning. This is our our results in application in terms of telecommunications. And thank you very much.
Maybe a very short question. Yeah. Hi, Paulo. Yes, thank you very much for this interesting works and the presentation. So regarding the, I have two quick questions, but I can ask it at the same time. So regarding this first work, the free space optical communication, is it single channel or multi-WDM system? And also for the second one, you said unamplified optical fiber communication system. So could you please comment what's the application scenarios of that one? When you remove that one, is it just try to reduce the cost, or it can be applied in data center, long haul, metro?
Yeah. Okay, that's the first one you are using for free space optics. You are using you cannot using several wavelengths, but you are using a single carrier. Okay, for the one I show you one for 1 terabit per second in a single carrier.
Yes.
Okay, but you cannot multiply this capacity in several terabit per second because you have a very wide bandwidth. So maybe also, I don't know if I have too much time, but let me show. Let's see if I think I have here one slide that I can show you. Yeah. Let me show you only. So let me try to share again. So this is one example where you can increase for multi-terabit per second capacity since you are using collimators, and the collimator you have a very wide bandwidth. This is one example. For example, you can use for all C-band, so you have a huge bandwidth that you can use it. And for example, you can use like high capacity current pluggables for different wavelengths. So by this way, you can increase the capacity. This is one of the experiments that we did. So in all C-band, you see only a variation in all the C-band, approximately 1.5 dBs. So you can you can use all C-band and also the other bands, just because they are this kind of collimators that they are transparent. So you can get here very high capacity using free space optics. The other question is for sure for data center interconnections. So there is a lot trend to reduce the power consumption, and if you can skip the optical amplifiers for short reach, and this the current system they becomes to come to short reach, because we need for energy and higher energy and more in the future. So you cannot use intensity modulation and direct detection. And so if you can remove the optical amplifiers, for sure you can reduce a lot of the power consumption, and also you can also the TCO, the total cost of ownership. Okay, so this is the reason that also the OIF is also try to avoid using these boosters for short reach.
Okay, thank you, Paulo.